I've been going on too long already, Alan, have I? Alan's yawning, so we, we, we better move on. Actually, the admin was so, all of that, the administrative arrangements were so excellently explained as you checked in this morning that I don't think there's anything for me to add to it. So I'm spared that excruciating session. And now we can go straight in. So yeah, it's a great pleasure to introduce Alex Vigoda from Georgia Tech, who's talking about colorings, and Ori's giving us the dope on that. Thanks, Sarah.
Okay. Thank the organizers for who are you waving to?
Yes, just making sure we run.
Oh. Okay. So everything, the talk's going to be about random colorings. And mostly I'll do a survey of some results about rapid mixing for the Glauber dynamics. And then at the end I'll do, I don't know, 0 to 20 minutes on whatever amount of time is left for some other results about the reduction from counting to sampling and how you can do the counting colorings faster, an improved reduction. So, okay, so the setup is we have a graph, maximum degree delta, and we're assigning colors to the vertices. We're looking at proper coloring, so we're assigning colors so that the neighboring vertices get different colors. And one of the setups we'll be looking at is when the number of colors is greater than the max degree, then it's trivial to construct a proper coloring. Anything you do, any algorithm you do will work, essentially. And so the question is whether we can generate a random coloring. So we want to sample from this distribution uniformly in time polynomial in the size of the graph, even though the number of colorings for this range of parameters is exponential in the size of the graph. So, okay. Now we're going to be, so the two things we're going to be looking at are counting colorings and sampling colorings. And we're going to be doing both of these things approximately because this exactly counting the number of colorings for this range of parameters is Sharp-P complete, which is a counting analog of NP completeness. So we can't do it exactly. So instead we want a FPRAS. We want a fully polynomial randomized approximation scheme. So I give you a graph and an approximation factor, and I want to estimate the number of colorings of the graph. That's supposed to be the number of colorings within a multiplicative factor, and I want to do that in time polynomial in the size of the graph and the approximation factor. And then this error parameter you can boost as close as you want just by taking the median of a bunch of trials. Okay? So this is a counting problem that we want to do, the approximate counting. And the sampling problem, what we want to do is, so our goal is to sample uniformly from the set of colorings. And we're going to get away with approximately uniform. So we're going to try to sample from a distribution which is within variation distance epsilon of the uniform. So it's just 1/2 the L1 distance is variation distance. And we want to do that time polynomial in the size of the graph and log 1/epsilon. So, and in principle, we might be able to sample exactly from this uniform distribution, but we're not able to do that here. Okay? And it turns out that these sampling and counting are equivalent in polynomial time sense. So if you can do one in polynomial time, then you can do the other in polynomial time. So, and I'm going to do later, so most of the talk I'm going to be focusing on algorithms to sample, and then at the end, second part, if I have any time, I'll look at how that sampling gives you an algorithm to approximately count. Okay. So, now to sample, what we're going to look at is this simple dynamics. So this simple Markov chain. So we're at some coloring at time t, a proper coloring. We choose a random vertex and a random color, And if that color doesn't appear in the neighborhood, then we recolor the vertex to that color. Otherwise, we stay where we are. Okay? Now, this dynamics is, for this range of parameters, it's uniform. I mean, it's ergodic. And so the unique stationary, and it's reverse symmetric, so the unique stationary distribution is uniform over proper colorings. And it also holds sometimes when you're below the max degree, for instance, for planar graphs. And so we'll be doing some in that framework too. Okay? And what we want to look at for this Markov chain is the mixing time. So we want to look at the from the worst initial state. We want to look at the number of steps to get within variation distance, at most a quarter of the stationary, of the uniform distribution. Okay? And our goal is to get this, the number of states, as I mentioned before, is exponential in the size of the graph oftentimes. And we're trying to do this in time polynomial in log the number of states. Okay? So what we're trying to address, well, so there's one maybe conjecture, I don't know if it's conjecture or not, but any possibility that maybe whenever this, so I said that it's ergodic with the unique stationary distribution whenever the number of colors is at least the max degree plus 2. And perhaps actually it mixes quite fast for that, whenever that holds. So we're trying to look at this possibility. Okay, now why does this, now so, okay, so this is ergodic in this range, but another reason of where that delta plus 2 comes about is from the phase transitions. Okay, so maybe this gives some intuition about why we might expect it to d plus 2 to be the right answer. So the phase transition that we'll look at is uniqueness. So in statistical physics, what's happening? Well, normally, I guess in statistical physics, oftentimes you look at the grid or the d-dimensional integer lattice. Here we're going to look at the tree because this seems to be the worst case graph in some sense. So what we're looking at is we're looking at a complete tree with branching factor d. And what we're doing is we're fixing a coloring of the leaves. And then now we fix the color of the leaves, and then we choose a coloring for the internal vertices, uniform from proper colorings, conditional on the leaves. So this is so we're choosing the internal vertices random, conditional on the fixed coloring of the leaves. And then we're looking at whether the leaves influences the root. So we look at the marginal at the root, and we ask whether the root is unbiased or not. Of course, for a finite graph, it's going to have some bias from the leaves. The question is, if I take the limit as the size of the tree goes to infinity, does the root still feel any bias from the leaves or not? So if for all sequences of colorings of the leaves, the root is unbiased, then we have uniqueness of the, it's uniqueness of the, when you're taking the limits, you're making a measure, you're defining a measure on the infinite tree. So we're saying it's a unique measure on the infinite tree. If you have some bias, then you have non-uniqueness. And it turns out that the threshold here for uniqueness is d plus 2. So perhaps that's why we might have the rapid mixing, this thing, holding up to d plus 2. Okay? Now another threshold, phase transition, comes in from this reconstruction. Okay, and maybe we can get some ideas from that too. So here, in this uniqueness, this is worst case boundary. Does it influence the root or not? Now, you might instead ask, well, maybe it's just some adversarial boundaries that influence the root, but most boundaries don't influence the root. So why do I care? So instead, what I might look at is if I put a random boundary condition, a random coloring of the leaves, and then I ask for most of them, or in expectation over the boundary condition, does it influence the root or not? This is what reconstruction is. So let me just illustrate how you do this. Because actually, I don't want to, so what does it mean, a random boundary? Random coloring of the leaves. So I don't want each vertex to choose a random color independently. I want to choose it I want to color the whole graph randomly, erase the internal vertices, keep that coloring of the leaves, and then go back and fix the internal vertices. So here's for the tree, it's easy to illustrate. So what I do, first I want to color the tree randomly, and then fix the coloring of the leaves, and then go back up. So this is what I do. So to color the tree randomly, I can just choose so here's an example. So I have some pretty pictures, that's the point here. So I got 4 colors. So I just choose a random color for the root. And then I just propagate it down by each vertex, choosing a random color different from its parent independently, okay? And I just propagate down. This is a random coloring of the tree. Now I just keep that coloring of the leaves and forget the rest. I fix that, and now I re-choose a coloring of the internal vertices conditional on that coloring of the leaves. And now I ask, is the root unbiased or not when I take the limit as the size of the tree goes to infinity? So more formally, I want to look at the expectation over the colorings of the leaves of the probability the root is unbiased or not when the size of the tree goes to infinity. So,
Eric, just one slight inconsistency.
Yeah.
Go back. You here, go back to, there we go. You're calling this d equals 2, but this is really d equals 3 in this
yeah.
tree?
Yeah.
When you say d, you really mean the maximum degree, not the branching factor as a rooted tree. Is that right?
I don't know.
I mean, because it makes a difference when you talk about threshold.
Yeah, I guess when I do d plus 2 it matters, but here I'm going to do like d over ln d,
Right.
but maybe
But-
Crept in about
But-
three slides ago,
Right.
I think.
But,
Yeah,
but I think what you mean is by d, you really mean the branching factor plus 1.
I guess so. I think for that uniqueness one, I think I mean d plus 1. Yeah.
All right,
That's the
so
max.
it's like
I think that's right. I don't know.
You really mean maximum degree when you say d.
Yeah, I guess so. I don't know. Anybody knows? Maybe you're probably right. I'm not sure. So, okay. So, so what's known about reconstruction? So this threshold, okay, so this is for a random boundary. Does it influence the root? So the threshold is going to be below the uniqueness threshold. When the number of colors is smaller than this d over ln d, then you can do a coupon collector type argument to say that if the neighbors were getting independent colors, then you would likely see all of the colors in the neighborhood when you're below that threshold. If you just did a coupon collector, so things are likely to get frozen. So that's why you'll get the root has some bias below there. But the other end wasn't known until recently. And so I think on Thursday, Nayantara is going to do this. Thursday or Friday or sometime. Is going to do this thing. And then Alan Sly is not going to do this. I think he's doing something else or not, or I don't know. But anyways, he got it down to the right threshold. So now it's known the reconstruction threshold for trees is at this d over ln d.
That's asymptotic.
Yeah, but actually I think maybe he's got the lower order term. Yeah, so this is all like 1 plus little o1 here.
So, but in principle, for each d, there's...
Yeah, maybe he's got the right thing though. Is he here? I don't know. You have the right thing, right? For all d or for a large enough d or?
There's still a gap between.
Oh yeah?
Smaller order.
Oh, okay. He can tell us in his talk. So, okay, so now how close are we to this d plus 1 for general graphs? Well, we're not so close, but we made some progress. So what do we got for general graphs? So we can I'll show this one when the number of colors is at least the max degree times 2 for any graph. We get n log n mixing. So n log n is roughly the best you would hope for because this is the time it takes to recolor every vertex at least once. Okay. Now, if you allow yourself a little bit slower, you can get a little bit below 2.
Eric, but that comment is a little confusing because you don't generally have to visit all
Oh,
the
yeah. Yeah, that's right.
in
Yeah.
order to mix.
Yeah. And so I should say that there is a Hayes Sinclair showed, I guess I should put it up there. If I had one of those scribble things, I could write it. So Hayes Sinclair showed a lower bound of n log n
Bounded degree.
when the degree is order 1. So yeah, so what Yuval was pointing out that actually you might think that n log n is a trivial lower bound because you have to recolor every vertex at least once, but maybe it suffices to recolor just a large subset, a random subset of the vertices, and then you might be random too. So, okay. Now, then after this, there was a, well, there's, with various conditions, you can improve upon this. And this is all a kind of program started by Dyer and Fries, had a nice idea, which people built upon. So I'll get into that, but the end result of those is that, well, you can get this constant down to 1, as close as you want to 1, but you have to make the degree big. And you see why this comes in. And you also need that no short cycles. Or if you want the degree to be small, well, then this constant goes back up a little some. So, okay. That's the best that's known there. Alternatively, we can look at that. That's kind of the uniqueness threshold. So then we might look at this reconstruction threshold and hope for graphs that are nice. Trees, planar graphs, maybe sparse random graphs. Maybe we can get close to this reconstruction threshold. That might be more the right answer there. So what can we do? So for planar graphs, we can get close to it. And this, I changed the game too. It's no longer n log n, now it's polynomial. So like this first one is n to the 4th or something like that, mixing time. So we can get close, and this is what I'm going to go towards today, is explaining this result, how you do the planar graphs. And also there's, so Alan Sly, I think it's talking about this one. So for sparse random graphs, you can get now within, to some constant, so the degree is, it's an expected degree constant, though the max degree is huge here in this graph. The max degree is log n over log n with high probability. But you would hope, or you would think that this should behave more like a degree d graph, since locally it's tree-like with expected degree d. And so they got down to some constant number of colors. And perhaps one might hope also for this sparse random graph that you could get down to this d over ln d too, maybe. Because on a tree you might think that you can get this d over ln d anyway. So.
Are these numbers to be taken with?
Oh, those thousands and hundreds are nice numbers. Yeah, actually, I
numbers
don't.
you made up.
Yeah, I don't know what the.
And is it linear in D, the last result?
Oh, this one. Actually, yeah, I don't know. I guess this 1,000 depends on d, right? Yeah. What is So I guess for every d there is a constant. Yeah. Yeah. Yeah, I guess that's not. Yeah, I guess it's not true at all. Whether it's what is it? Don't take it too literally. But this one is. This is just some. These are more likely to be right. Those are some constants, but I don't know if 100 and 1,000 are right, or there should be some more zeros maybe.
People are used to probabilistic proofs, but probabilistic statements.
Yeah. Yeah, just making life easier for the talk. So, okay. I'm sure there'll be a lot more simplifications in the talk. So, what am I going to do in here? I'm going to try to show the idea between this, for this last result, where we do the planar graphs, down to d over log d. And the nice thing about doing that is that along the way, I'm going to go through a whole bunch of results. So I'll go through this easy one, or not easy, this clever idea of Mark's.
Very.
This first one, and then I'll talk about Dyer and Fries's idea to improve this, and then some improvements from that, and some result of Tom Hayes for planar graphs, and then once we do all those, then the last thing is easy. So, okay, so this will be the plan. I'll go through these, boom, 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 these results here. Okay, so here's the setup for the 2 delta. Oh, D and capital D and delta are the same during the talk. This is a merging of several talks. So, okay, so here's the general setup. I'll go quickly. Just we're going to do coupling. So we have just 2 distributions that we want to. If we define a coupling is just a joint distribution. So it's a distribution on the product space, so that the marginals. So if I just look at the first coordinate, it looks like the first distribution. I look at the second coordinate, it looks like the second distribution. If the marginals are correct, then it's called a coupling. And the point is that if I take any coupling and I look at the probability they differ under that coupling, then that gives me an upper bound on the variation distance. So now what I want to do for Markov chains, well, I want to bound the mixing time of this dynamics. So I take one copy of the Markov chain, which is in the stationary distribution, one copy starting from an arbitrary coloring, and I want to run these things in some correlated manner so that I can upper bound the time till they coalesce, they reach the same state. Once they reach the same state, that means this arbitrary chain has reached the stationary distribution. So that means it gives me a time, an upper bound on the probability they've differed, so that probability I've differed, I'm not in the stationary distribution, so it's an upper bound on the variation distance, so I want to just get this below 1/4, because I was trying to get some sampling algorithm which is within variation distance 1/4 of uniform. Okay, so how do I do this? Normally what we do is we look at some distance measure, so we take an arbitrary pair of colorings, and we're going to look at their distance. We're going to define some joint evolution for one step. So we evolve them both in some correlated manner for one step so that the expected distance will contract. Okay? If we do this, then we know the expected distance at time t will go down by this multiplicative. And so if we put in the max distance there, and then we take the time as this, then we got the expected distance is at most 1/4. And then since the distance is at least 1, we can just apply Markov's inequality, and the probability they differ is at most the expected distance. So later I'll do some other distance other than Hamming distance for planar graphs. And then the key point to do this last step is all I need is that the distance, to apply Markov's, I just need that the distance is at least 1 to apply Markov's. Okay, so. Okay. Now to make life a lot easier, we use this path coupling framework of Bubbly and Dyer. So what happens here is I wanted to define a distance for every pair of colorings. Here I want to apply, define a coupling for every pair so that the distance contracts in expectation. Well, it suffices if I define a coupling for pairs of colorings that only differ at one vertex. If I can do this for all pairs that differ at one vertex, then I can create a coupling so that for every pair of colorings, it also, the coupling contracts for that coupling I create. Okay, so how does that work? So if I want to So I have a coupling for every pair that differ at one vertex. Now I want to create a coupling for every pair of colorings. How do I do that? Well, I take my pair that I want to couple, which maybe differ at 100 vertices. 100 is just an arbitrary number again. See? So. Okay, so I take a pair that differ by this 100 vertices. Now I look at the path between them of distance 1 vertex. So along this path, each pair along the path differs by just one vertex.
You fix arbitrarily for each pair such a path.
Just take any path where the distance is exactly the Hamming distance. Okay? Yeah, it doesn't matter which one you choose, which path you choose. Now, what do I have? I have my hypothesis of this lemma was that for every pair, for every edge on this path, so every pair of colorings, this is a pair of colorings that differ at one vertex. So for each such pair, I have a coupling of them. So now what do? Now I'm going to apply that coupling. I'm going to compose that couplings. So what do? I first choose a random move for this first chain over here. That first guy or girl. Okay? Now I have a coupling for that pair. So once I have a move for that first one, that coupling tells me, given the move for the x, what's the move for z1? Okay, now I have a move for z1. Now, once I have a move for z1, this coupling of the second pair there tells me, given a move for z1, what's the move for z2? Okay, so now I have a move for z2, and I so on, boom, 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 boom. Yeah. Anyways, and so I keep going along the path, and finally I got a move for y. So given the move for x, I got a move for y. Now, so that gives me my coupling, and now I need that the coupling contracts in expectation, the distance. So I look, what do? I want to look at the distance of these two endpoints at the next step. So it's just the sum of the distances along the path. I do linearity of expectation. Now for each of these guys, this was just the coupling that I had from the hypothesis. So, and then each of those contracts. So that's from the hypothesis as a lemma, and so then this whole thing contracts. Okay, so linearity of expectation. So it's a good. I defined a coupling, and it's a good coupling. The distance contract in multiplicative sense. Okay, so now all we have to do is we have to look at a pair of colorings that differ at a single vertex and define a good coupling for them. So I have this colorings here. They only differ at z. And z will probably change to v by that. So, I don't know. And anyway, so the rest of the graph is the same in both colorings. Now, what's my coupling going to do? Well, the obvious thing to try is that they both try the same vertex and same color to update. So I choose one vertex, one color. They both try to update this vertex v to this color c. Now, most of the time, it's going to work or fail in both copies, in xt and yt. Okay, so if I'm coloring some vertex over here, then it works or fails in both, so that vertex is going to look the same after the move in both. It looks the same before, it's going to look the same after. The only time things might differ is if it involves z or a neighbor of z. Okay? So now if I color a z to some color yellow, which doesn't appear in the neighborhood, then z afterwards is going to become yellow. It's going to be the same in both, so my distance went down to 0. Okay? So the number of such moves, these are my good moves, is the number of colors that don't appear in the neighborhood of z. So that's the number of available colors for z. Alternatively, now I have some bad moves. Namely, I might try to recolor a neighbor of z to this green. In which case, in this scenario, the top chain makes it green. The bottom chain stays brown because it's blocked. So it failed. So I get another disagreement. So my distance goes up to 2. Similarly, I can do the same thing with red. And in red, the bottom works, the top doesn't work. Okay. But if I try this guy to pink, then pink works in both. It only matters if I try green or red. That's the only thing that matters. So I have for each neighbor of Z, I have these two possibly bad colors. So that means I have 2 delta bad colors at most, and I got number of available colors which are good. The number of available colors is at least k minus delta, because I have at most delta colors in the neighborhood. So I got good has to be bad, so I need k minus delta has to be 2 delta, so I need k to be at least 3 delta. And then the distance contracts a little bit, and then that's it. So that's 3 delta. I promised you 2 delta. This time that constant does matter. So what do? So I instead, if you look at the coupling, then before, I'm going to do something that's slightly non-trivial, slightly not, it's not the identity, just for this one move. So if for this neighbor of Z, whenever I try green in the top chain, I'm going to try red in the bottom. If I try red in the top chain, I'm going to try green in the bottom. Everything else is the identity coupling. Everybody tries the same thing. So now the point is that if I try red in the top and green in the bottom, it doesn't work in either one. It's blocked in both. And here, if I try green in the top and red in the bottom, it works in both. So this one becomes, the distance goes up by 1. So this one doesn't hurt me at all. This one might hurt me. So now there's only one bad move for each neighbor of Z. So that means then I just have to beat delta now. Instead of 2 delta, so I just need k bigger than 2 delta. So that's it. Okay. So that's the 2 delta. Oh, now I'm going to do this. So this is diaphragm. I'm just going to do a slightly simpler view of it. So it gives me, when the degree is huge, then just assuming the graph is triangle free, I can get a little bit better than that 2. Okay? So how do I do it? This was the scenario. I needed the number of available colors for this disagreement to beat out the number of neighbors which are the bad moves for him. Now this available colors, I just use k minus delta here. But typically we would think that, in a random coloring, I'm unlikely to see delta distinct colors in the neighborhood. And so that's what we're going to do. We're going to prove for triangle-free graphs that you're unlikely to see delta distinct colors in the neighborhood, and therefore the number of available colors is much higher. And then we get some better result. Okay? Now, what's the best we could hope for in the neighborhood? Well, if the neighbors were each choosing IID colors, then the number of colors that does not appear in the neighborhood, well, the colors that are appearing there, it's a binomial distribution. And so if we look at the expected number of colors that are appearing there, that are not appearing there, this is the chance it doesn't appear in any of the neighbors. And then it's the expected number. So anyways, it's roughly that for large delta. Okay. So this is if all the neighbors were choosing uniform colors independently of each other. Well, that's not the case in general, but if we look at a triangle-free graph, actually we're going to get something close to that. So what's the idea on a triangle-free graph? So you give me a random coloring. Now if you give me a random coloring, what can I do? I can take any vertex and recolor it by one of these Glauber moves. So take any vertex, erase the color, re-choose it, conditional on its neighbors. It was a random coloring before, it'll be a random coloring afterwards. So now I have a triangle-free graph. So what I want to do is I want to do that same process, but on all the neighbors of this vertex that I'm looking at. So I'm going to simultaneously erase, you give me a random coloring, I erase all of the colors on the neighborhood of that vertex, and then re-choose them.
And on the vertex Z or no?
No, just on the neighbors, yeah, not on Z itself. So there's no edges on the neighborhood because it's triangle free. So I can simultaneously re-choose the colors for all of the neighborhood, and they'll all be independent of each other when I re-choose for them. And then I can look at so then what I'll argue that no matter what it looks like outside the neighborhood, so you fix however you want, it's not even a random coloring, just arbitrary coloring outside the neighborhood. For every coloring outside the neighborhood of Z, Well, no matter how you fix it, when I re-choose the colors on the neighborhood of z, I'm not going to have too many colors appearing there, okay? So what do? I just look at the indicator function for the probability this vertex, this neighbor, is a color C. Then I can write the number of colors that don't appear in the neighborhood of Z as this sum product, right? And no neighbor's got that color, and then I count how many colors don't appear there, okay? So then I have the expected number of colors given what's outside of this neighborhood of Z, is this thing. Now I just do an arithmetic mean, geometric mean. I get it like this, and then I just rewrite it. I just swap this colors, and this colors becomes the number of colors that are available, okay? So I get like this, and then this thing is asymptotically, for large delta, is roughly this, okay? Which was the same thing as that we had before if all of the neighbors were choosing independent colors. So, and all we needed was that the number, the only thing I didn't tell you was that to get this, we just need that the number of available colors for each of these W's is at least 2. Otherwise, I cheated. So if it's at least 2, then for large delta, it's roughly that, okay? So to be at least 2, I just need k at least delta plus 2. And no matter how you fix f, this cal f, then I have it. Now also, this is the expectation, but all of the neighbors of z are choosing independently. So I can apply a Chernoff bound so that when the degree is big, then I get with high probability that this holds. It holds for every f, so therefore it holds for a random f, okay? And I get with high probability when I do that, okay? So that means with high probability, every vertex has a lot of available colors.
Is it okay to use max degree here, or don't you want this to be true for every vertex?
Yeah, but if it's got fewer vertices, neighbors, it's even better for you.
Okay.
Yeah, so. So before, I had k minus delta. I had to beat delta. Now, when I assume the degree is big, I can replace that k minus delta by this k e to minus delta over k has to beat this delta, which means k, you solve this thing, and this means k has to be bigger than 1.76.
So this is, what you just did is true for the uniform coloring.
Oh, yeah.
I'm interested in the convergence.
Yeah, that's true. Yeah, so I cheated. So the short partial answer is that you just need it for one of the chains. Actually, if you do the coupling analysis carefully, which actually I'm going to do later, is you just need that one of the chains has the right number of available, has a good number of available colors. And even if the other chain is arbitrary, then it's okay. And so now one of the chains I can think of is coming from the stationary distribution, and one of the chains is arbitrary, and I'm just trying to couple with the stationary.
Even though you have the path coupling.
Oh yeah, so I have to not do it with path coupling. That's why I didn't do it. But I'm going to not do path coupling later. So yeah, so I have to do, if I don't do path coupling and I take an arbitrary coloring and a random coloring, so the random coloring is going to be nice, and it suffices that the random coloring is nice. And then it just needs that. It's lucky. I don't know why it works out like that. So I don't know. It makes life easier. But that's only for that 1.76, and then to get below that 1.76, you have to use additional properties, and then you need both chains to have the properties, and then it becomes a mess, and that's why I'm not doing it. So
just so I understand,
Yeah.
so it's not really necessary that the graph have large maximum degree. The point is this delta plays two roles. On the one hand, it's an upper bound on the maximum degree of the graph. On the other hand, it's the thing that you get on the right-hand side.
I think
the
maybe
lower bound for the number of colors.
maybe it's better to say, if I said that k has to be at least omega of log n. Maybe that's better. That's probably clearer
Right.
next time.
But that, no, but then,
Yeah.
yeah.
Yeah, I think it's when you're doing turnoff, you probably get a K in there. It's probably, that's the number of random variables is, because we were doing some,
Right.
we were counting how many colors don't appear, so. Okay, so that was, the degree was huge. So we could do we could have a high probability statement about what a random coloring looks like. Now I just want to do some idea about what you do when the degree is smaller. So now, okay, so I'm just going to give a little bit of about this, how you can get the degree down to smaller. Okay. Yeah. Now, what is it? So the first thing we're going to use is that, well, Hayes showed that actually this dynamics also, you can, if you start from any coloring, you run for order n steps, then you're going to recolor most of the neighborhood, or a lot of the neighborhood of the vertex. And if k is at least delta plus 2, then all of those vertices are going to have at least 2 color choices, which is the sort of thing we needed in that proof. And then you can say that most of those choices are roughly independent of each other, so you'll still get the right number of available colors. Okay. Now, I'm not going to go through this, but I'm going to use this to then argue how we can go to constant degree. So, because even with this is saying that, well, so now if the degree is log n, then, well, everybody's going to after order n steps, everybody's going to have a lot of available colors. But if the degree is order 1, then you only have it with some large constant probability that the neighborhood is nice. And any neighborhood you want to look at, you know, everybody's color 1, or everybody's 1, 2, 3, 4, 5, 6, whatever you want. Any neighborhood you want, there's some constant probability that that'll appear in a neighborhood in a random coloring. And so you're going to get order n, omega of n vertices that are going to look, their neighborhood's going to look like that. So there's going to be a lot of vertices that are going to have a bad neighborhood, no matter what we do. And what's going to happen is that our disagreements in our coupling are going to be correlated with where these bad neighborhoods are. So, okay. Yeah, so our disagreements are correlated with these bad neighborhoods. So what are we going to do? So what we're going to do, but the point of this lemma, it tells us that actually we just have to recolor, no matter what the distance 2 looks like, if we recolor most of the neighborhood, then it's going to get the right number of available, it's going to have a large probability of getting the good number of available colors. So we just have to wait order n time. Even if it's bad, we wait order n time, and it's likely to be good. Likely with constant probability to be good. Okay? So what do? So we take a pair of colorings which differ at single vertex, sort of the path coupling framework. Any pair of colorings, okay? So it could be initially I have this vertex and it's, yeah, so this pink, it's supposed to be pink or red or something. This is frozen sets. So these are kind of, you have this disagreement. It's likely to be frozen around it. Now what you're going to do is you're going to just look at some local ball around it. I'm just going to look at some constant distance around it. I'm going to run these chains for order n steps. If I run it long enough, or the constant's big enough, then every vertex in this ball has large constant probability of becoming uniform. Its neighborhood is likely to be the right number of available colors. So I'll run long enough so that every vertex in this ball is likely to have this uniformity property, the number of available colors. Meanwhile, I've defined the ball big enough so that this disagreement, well, it's going to start escaping. It's going to move around. So, and I don't really have any bound on how fast it's moving. Well, I have some bound on how fast it's moving, but it's going to move fast because there's a lot of vertices that are frozen. Oh, they're not actually frozen, actually. I think nothing's frozen. K is bigger than delta, actually, here. So it's not frozen. It just means that it doesn't have K e to the minus delta over K available colors. It has more like K minus delta available colors. Okay? So it has few available colors. So the disagreement's going to spread faster through these pink sets. Okay? So what I do, though, is I can just bound. You can define the ball big enough so that the disagreement won't escape from the ball, but meanwhile you're likely to have everybody in this ball to have the right number of available colors, or a good number of available colors, and then you're all set. So what happens is you run for order n steps. The disagreements have moved around, so here they moved, but they're still contained in the ball, and meanwhile you're likely, with some large constant probability, oh, I don't know why I put this slash. So you're likely that this whole ball is all uniform. Looks nice, and then you're all set. So what you get is, so the chance that the disagreement is going to escape from this ball, well, this is just this is called the passive disagreement argument. So, they propagate at rate 1 over K minus delta, because that's the number of available colors on vertices in the worst case. So, anyways, it's an easy argument to say that it's unlikely to propagate outside the ball. And then also, then I just do a union bound. Each vertex is likely to be uniform. And then I do a union bound over the vertices. And then, so it's likely that everybody in the ball is uniform. And then that means that with this probability, everything's nice, which means that I can use this nice bound on the number of available colors. And then the distance is going to contract from then on. And with this small probability, things are bad. And the distance grows in expectation, but it doesn't grow too much. I still have a K minus delta there. You just trade off these two things against each other. I just have to run for now order n more steps. And if I'm in the good scenario, distance is going to be really small after another order n steps. In the bad scenario, it's grown, but that's only with an e to the minus r. So you do whatever you do, and you're okay. So that's the rough idea for that. But now I want to go to, now Tom Hayes had this nice idea for planar graphs. How do we get, so it's a slick way to get down close to the max degree for planar graphs. We don't have to use any of this uniformity stuff for what he's about to do. Okay? I'm going to change the dynamics too, actually. I'm going to look at this other version, and then so I'm going to look at this version. So I choose a random vertex, and now that vertex, I just choose a random legal color. Okay, so I look at the neighborhood, the colors that don't appear, and I choose randomly from those colors that don't appear in the neighborhood. Okay? It just makes it a little easier to analyze here. And now I'm going to look at a general coupling. So this isn't path coupling. This is any pair of colorings. I want to analyze the coupling for it. So I have at time t, I have the disagreements. Now, if I ask, so what am I going to do? Each vertex is going to choose the same color, same vertex to recolor, and they're going to try to maximally couple, try to choose the same color to recolor them, that vertex. Now, so if the color, this is available colors for x, available colors for y. So if the color is available for both, well, one chain is going to choose that color with 1 over its number of available color. The other one is choosing it with the other one. So I got the min of those two probabilities is the probability that both chains can choose that color to recolor. Okay? So that's the chance that they agree with color C at that vertex. The chance they disagree is just 1 minus that, which is just this thing. Okay? And now I take this thing. So the numerator is the colors that are available in one and not in the other. So that's upper bounded by the number of disagreements on the neighborhood. I want colors in x and not in y, or in y and not in x. The number of such colors is at most the number of disagreements on the neighborhood. So I get this numerator, and then in the denominator I get the max of these two things. So actually this was the earlier question about why I just need one of the chains to have this good bound on available colors, is because of right here. I just get the max there in the denominator. So, okay, so I have this. This is the general coupling. Now, what can I do with this? Now what I'm going to do is I'm going to change the distance. So instead of Hamming distance, I'm going to give each vertex a weight. Now, and I'm going to look at the weighted distance, okay? Now I want to analyze this weighted distance. So what do? So I want to look at the expected distance at time t plus 1. So I just ask, well, given I update vertex v, I just say, well, I just look at its weight times the probability it disagrees at time t plus 1 minus was it a disagree at or not at time t. So this disagree at time t plus 1, and this is what I just wrote there. Okay, so I have this expression. So I just, okay, now I sum over all vertices and I get the difference in distance between t plus 1 and t. Okay, it's just this thing. And now I just redo this sum. So I take out this neighbors of v and just write it out. So I write out the sum over all disagreements of their neighbors. Okay, just switch it. Okay, now what do I got? Okay, so this is what I have. And well, you can view it. There's some way to view this intuitively, why this makes sense. Because what's happening is I choose a random vertex. Now, if it was a disagreement, well, first uncolor it. And then you take it out of the disagreements. That's what's happening there. So that's why you get a minus the disagreements. Now, I ask, does it become a disagreement after I recolor it? So the chance it becomes a disagreement after I recolor it is, well, there's got to be some neighbor which is a disagreement which causes it to become a disagreement. So that's sort of what happens, okay? But then the punchline is that, okay, so if I have some uniform bound on this available colors, I can take that out. Say I have k minus delta there. I can just replace that by 1 over k minus delta outside. Now what do I got here? I got the adjacency matrix here times this vector w. So I'll take w to be the principal eigenvector, okay? So I take the largest that should be eigenvalue. So I take the largest eigenvalue of the adjacency matrix, and then I take the corresponding eigenvector with non-negative values, okay? And then, now what do I got here? So that's my weights on vertices. So then that means that when I'm applying this adjacency matrix there, it's contracting by rho, okay? So why is that interesting? Well, then that means that I want this thing to be positive. So I need rho to be less than this k minus delta in the denominator. So an example is, if it's a planar graph, then I know the adjacency matrix, the maximum eigenvalue, is in most square root delta. So then I just need k minus delta. So I just need k minus delta to beat rho, to beat square root delta. So I just need k to be bigger than delta plus square root delta.
So the point here is you instead of using maximum degree, you're using the spectral radius, which is in general lower for the bound on a min.
Well, you're using this clever distance.
Yeah.
Well, you're changing from uniform distance
to this.
Right.
This,
and by doing so, you're pushing down.
Yeah.
I mean,
It's
it's easy to see that precisely using the uniform vector,
Yeah.
you can see that the spectral radius is less than or equal to the maximum degree.
Yeah.
And what you're showing is by using a cleverer vector, you push it actually down to
Yeah.
the spectral radius.
Okay. Yeah, let's finish up soon. Another hour? Okay, so let me just quickly do something. So what do we had here, now I used here that a min was k minus delta, and so I want delta, square root delta to versus k minus delta. But I had all these ideas about k minus delta shouldn't be k minus delta, but it should be k e to the minus delta over k. That's all I want to do here. So how do I get that? The point would be that, you know, if things were really independent on the neighborhood, I just need k to be about delta over ln delta, and then I can beat delta to the 1 minus epsilon for any epsilon, okay? Just changing the constant up there. So how do I do that? So now first off, if the degree is huge again, or big, I shouldn't say huge. If the degree is big, then I can do it for planar graphs. This is a planar. Should say, oh no, okay, so it says the spectral radius is small. Okay. How do I do it? Well, the thing is, if the spectral radius is bounded, then what I can do is I can take this graph and draw it into something. It's not a tree. We always call it a tree-like thing, but so the point is that I can make it into levels, so that every vertex, most of its neighbors are below it, and it's got relatively few neighbors up. Okay, and then the point is that to prove this available colors, I start at the leaves, or the bottom level. So I can ignore the up neighbors because those are relatively few. And now I assume that the down neighbors already have this uniformity property, and then I use that to induct and apply this kind of same sort of lemma about, re-choose the neighbors randomly and same
So here
thing.
you're not using the usual Glauber dynamics, but updating according to this order.
Well, this is so far I'm just using the Glauber because I'm assuming high degree. So I'm going to get for every vertex this thing, yeah. But this is high degree. Now then the question is, how do I get it for constant degree? So when it's high degree, I can just create this graph, and I can just prove using this level sets that with high probability and a random coloring, it's nothing about the dynamics, everybody has this property. Then I want to go to, so this is what the levels are. What I do to get the levels, I just look at the eigenvector and I break it up based on the entries in the eigenvector. Okay, I just look at it different ranges. Okay, and then the point is that by breaking it up in this way, easy algebra, and it gives you that for a vertex, most of its neighbors are below it. It's got few neighbors that are up. Okay. Now, then I want to look at graphs that have constant degree. Now in here, I'm going to have the same thing that a lot of there's going to be big chunks of frozen. And the problem is that Glauber takes a long time to get rid of these frozen chunks, because what happens is I have to start at the bottom and get the right number available and work my way up. And these frozen chunks might have depth, say log n, so it's going to take me n log n time, and that's too long.
You mean really frozen now, or just?
Yeah, now I mean
cold?
really frozen. Yeah. Before I just meant
Cold.
cold. Yeah, and here I mean really frozen or cold, or yeah. But it could be really frozen actually. Yeah. So they can't actually move. And then the only way I get a move up there is by unfreezing, and it's got to work its way up. So what we do is we look at this other dynamics.
I'm sorry, and the fact that this time is n log n rather than just n.
It screws up that whole other argument where I had that ball around that one disagreement.
It doesn't just screw it up by making the time a little bit bigger.
No, because
Totally kills the argument.
yeah, because if you have what I used is that if you run for Cn steps, then a disagreement is going to propagate at most e to the c steps away. But now if I run for log n, then the disagreement is going to propagate, some poly log n, and then it's going to spread all over, and then I got to look at getting uniformity all over, and I don't know what the hell to do. So we don't know how to analyze Glauber, actually. That's the interesting question. How to analyze Glauber directly. So we cheat. Well, we don't cheat. We had a clever idea, or I'm supposed to say, okay. Anyways, we changed the game. So we look at this other dynamics, which is this level set, which is the same thing that we use to prove the uniformity in the high degree case. So the dynamics works by recoloring the bottom level, and then it recolors the second level, and it works its way up by these levels based on the eigenvector. And then in that way, by the time you look at a vertex at this level I, you've gone up level by level, so that vertex is likely to have the right number of available colors because you did it in the right way. Because the dynamics works exactly the way you want to prove this uniformity property, so it helps you. And then you can use something like we did before, and you get that this dynamics mixes after just polylog rounds, and then you can compare to say the Glauber is not that much different. But what we don't know how to do is analyze Glauber directly for this tree. And that seems useful maybe to analyze random graphs or just, you know, to get a better bound on the mixing time and understand what's going on. So.
Any quick questions before we grab some coffee?
Planar graphs, isn't the real issue that the maximum degree is a lot different from the average degree?
Yeah.
I mean, in the
Oh, yeah.
for sort of sparse
Oh,
random graphs, the
Oh.
aim was to get the
Oh.
average degree. Do you think?
Why do I think that it's delta over log delta? Is it you're asking, or?
Yeah.
I guess just for the simple reason that it's, you know, locally it looks. I think this Poisson tree, you know, if you did a tree where each vertex has its degree is Poisson, then it should be, then its average degree D, and it should behave like this degree D tree, and the sparse random graph is locally like that. So that's why I thought it should be the D over log D. No, nothing clever about why, but I guess. You could put it. I guess also you could look at the reconstruction threshold on a random graph instead of on a tree. Ask about influences, and a lot of times the reconstruction threshold on a random graph, GNP, corresponds to the one on the tree. So maybe that would be better insight.
Eric, I think the question is
Yeah.
on random graphs,
Yeah.
muscle and slack, so
Yeah.
you can do you can do better. That is, you're not the degree over the max degree is not the relevant parameter.
Oh yeah, but here I didn't write max degree. I wrote the expected degree. Yeah.
Right, but for planar, but the question, as I understand,
Oh, yeah.
for planar graphs, you were talking about the max degree.
Oh yeah. Oh yeah.
And one
Oh yeah. And then.
for an improvement there in terms of some averaged quantity.
You're saying for plane. Oh okay. Sorry.
Well, I'm just trying to interpret.
Oh yeah. Okay. Okay. Yeah. Yes. Whether you could use like get a constant number of colors or something like that. But I guess I don't know what dynamics to do. I guess is the question. So because on a tree, this Glauber already is slow below D over log D. So a tree is an example of a planar graph, and
What is slow?
hmm?
What is slow? Still polynomial or?
Yeah, it's slow. It starts to become slow once you get below D over
No,
log.
that's slow. It's always polynomial on the tree.
Well, I guess it's going to be, if it's C, D over log D, it's going to start to grow. It's going to be, the polynomial is going to grow with C. But if you're little o, D over log D, it's going to be, maybe if it's constant degree, then it's just going to be super polynomial.
But,
Yeah. Yeah,
but-
okay. Yeah.
Alan's
Oh,
keen,
yeah.
so I'll let him
Yeah.
know.
Was it- So you've been talking about Glauber dynamics or things related to Glauber dynamics where you recolor either a single vertex or a small neighborhood. An alternative that physicists use a lot is the Wang-Swanson-Kotetsky or Kempe
yeah.
chain dynamics, where you recolor, starting from a given vertex, you would recolor a fairly big and in general unbounded
Yeah.
cluster. Are there any results
I
on
don't
that
know.
kind of dynamics?
I mean, and that's why I asked for bipartite, whether there's something like that you could use to get below D.
Right, so for example, for bipartite graphs, that dynamics is ergodic.
Yeah, it's already,
Always.
Yeah, nothing really known. So you could potentially, but then this spectral radius stuff doesn't come in, doesn't work, and then we don't have any idea how to get to below D other than this spectral radius idea. So, yeah.
Okay, so let's break there.
Oh, yeah.
Yeah.